Hey there, this is going to be a supplement to a recent video we did where we looked at maximum likelihood in the context of the Ornstein-Uhlenbeck model. We've been going over some of the chapters in the book Optimal Mean Reversion Trading, and I'll put a link to the exact title and the authors in the description below. And I got a comment saying that someone was not really clear on the whole maximum likelihood estimation thing. So I usually do programming things, mathematical, numerical methods, and that sort of thing. But in this video, I just kind of want to go over, in a very hand-waving, non-rigorous sort of way, kind of the mathematics behind, and create an intuition as to how maximum likelihood estimation works, kind of what the parameters we're trying to pull out of the estimation mean, and also a bit of the other mathematics that is involved in the actual derivation. So basically, how you would go about finding the maximum of a function of one or many variables in this case. I'm not going to spend a lot of time on that because that's basically just first semester calculus, so I'm just going to kind of breeze through that and then spend more time on the actual statistical part. And again, this is not going to be very rigorous. I just, as I said earlier, want to create this kind of intuition so you understand what we are trying to do here. So having said all that, let's get into it. So this was our notebook maximum likelihood estimation. We started with the normal distribution. We just kind of showed how you would do the likelihood for a bunch of variables. And then just kind of said that we could get the mu and the optimal standard deviation, the mu and sigma from these formulas here, which in the case of normal is pretty simple. It just turns out to be the sample mean and the standard deviation. And then we moved on to Ornstein-Uhlenbeck. I think one of the issues might be notational because this looks a lot more complicated here. For the normal distribution, I had just written f of x, and the author uses a kind of complicated notation here that I don't particularly like. What they mean by this is that everything to the right of this semicolon here are parameters that you are given or that you know beforehand going into the problem. And everything to the left of this are inputs to your function. So these are things that you're measuring as you go along. For example, in this case here, we're talking about pairs trade. So this is the price at, say, day one, and this would be the price at day two. So you're kind of measuring these, and then you're plugging in numbers, assuming that you know these to get some sort of output. Now, I did not use this notation up here. So let me copy this formula into a new notebook and show how we might write that in the format that they did, and then let me show how we want to flip the problem around notationally when we do the maximum likelihood estimation. So we're going to kind of interchange. Where is this equation? We're going to interchange the positioning of these things. So, okay, in a new notebook, the only coding I'm going to do is just for visualization purposes here. So we're going to copy and paste our normal distribution formula from the previous notebook here. So to use their notation, the way I might write this is instead of just f of x, I might write this as f of x semicolon mu comma sigma. So f of x given mu or sigma, or you could read it as f of x parameterized by mu and sigma. In other words, I know these two numbers, and then I'm measuring x's as I go along and plugging them into my formula to get an output. So as a more concrete example of this, suppose, I don't know, you're at a university and you measure the heights of a bunch of men at the university, and you wanted to know where they fall on this bell curve compared to the mu and sigma for the typical American male. So for example, if you look in the literature and mu happens to be equal to 175 centimeters, which is about 5'9" I have no idea what sigma is. Let's just say it's 5 centimeters. You could calculate the value of f just by plugging things into this formula given a height. So you measure a height, say x is equal to, I don't know, 170, and in Python we could use the norm function norm PDF to get back this value. So let me make sure that has run. We could just say norm.pdf x mu sigma, and we could get a value if I could type correctly. I don't know what that is. Sigma. Okay, so I fixed my ever-present typos, and we get back a value. So, and again, this could be done for like several samples. So if we had 170 and 190, we get back to, and it just tells you where the specific heights fall on this curve. But now, if we want to reverse this problem, so I'm going to take this and I'm going to copy all this formula here. Select all. Let's come down here, make it a markdown cell, paste it in. We want to swap this x and mu and sigma. So let's just take x. Let's see here. Where is x hiding? Semicolon x. So we want to investigate problems like this. We're given some heights x. So for example, to continue with this analogy, we go to a different country, say the Netherlands, where people I think are on average taller than in the States. And we want to find out what mu and sigma are given a sample of a bunch of heights. So we already know x. We go there, we look it up, we look up a bunch of heights, and now we need to figure out what mu and sigma are. So, kind of like in linear regression, there's no exact solution for this, generally speaking. So it's a statistical process, so we're basically coming up with a best estimate for mu and sigma. So now I just want to develop an intuition as to why we say maximum likelihood. And for the sake of reproducibility, I'm going to set a random seed, so np.random seed is equal to, I don't know, let's just pick a number at random, say 31. And now I'm going to plot out, I'm going to choose a mu and sigma just for demonstration purposes and kind of plot out this function here. So I'm going to choose mu to be 2 and sigma to be 2, and I'm just plotting this out. We get back a bell curve. And I'm just going to choose 10 points at random that are kind of normally distributed and kind of plot them along the x-axis down here. So let's choose 10 points. I'll set a variable that we can adjust if we want to do more or fewer points at some later time. So I'm going to set 10 points. So here are these random points, again, distributed mu equals mu and sigma. Just plotting them, and I'm going to just kind of center the x-axis about these, the values kind of defined up here. So there we go. In fact, let's draw vertical lines to see where they intersect this black curve. So I'm going to loop over my x's and draw a bunch of dashed vertical lines that kind of intersect with the solid black curve. So there we go here. Let me just rerun my seed command and plot this out. So as you can see here, most of these values happen to be kind of left of center here. They're all kind of clustered middle-ish. You have someone slightly more to the left here, and then there's one outlier to the right. And notice that all of these values where they intersect this black curve are fairly high. You got a bunch very close to where this function, this black function, solid black function, is a maximum. You have some that are a bit lower, and then you have one guy that's not particularly relatively low value, not particularly high. So let's just rerun this block again, set a different set of random numbers. Okay, now the outlier is to the left here. It's not particularly high. Most of them are centered again around the maximum value here. There's a couple, where the function's still relatively high, but, again, the bulk of them are near the middle. Let's just do it one more time and see what we get. Okay, you can kind of see a pattern developing here. Again, the bulk of them are where this black line is near a maximum, and a handful of outliers. So, not to beat a dead horse here, but if you're given a point, you can kind of assume that since they tend to be near the center of the distribution where the function is a maximum, or given a collection of points, you can kind of assume that you're near the center and near a maximum. So let me type this out down here, and then let me talk about how to determine where the maximum is located. Since points seem to cluster where the likelihood is a maximum, we will choose our mu and our sigma such that we maximize the likelihood given our observed data. So for example, just if we were given this set of data here, it wouldn't make much sense to choose a mu of -4 since the likelihood is very low at that point. So we don't want to just choose points at random and do it by trial and error. How do we find the maximum of a function? Well, that's just basic first semester calculus. We take the derivative of a function, which is right here, with respect to the variables we're interested in, which is mu and sigma, where the sigma appears twice here. And we would set that equal to 0. Set it equal to 0, and then it's just an algebra problem. We would solve those resulting equations for mu and sigma. So I've added that in text down here. We just take the derivative and set it equal to 0. Now the next thing is we don't have usually a single point. You have a whole collection of points. So what is the likelihood of a collection of points? Well, the way to think about this is think of it in terms of probability. If you had like a regular six-sided fair die and you rolled it a bunch of times, say 5 times, what are the probabilities of getting 5 sixes in a row? Well, it's just the probability of each individual occurrence, so it's 1/6 to get a sixth. And then you multiply 1/6 times 1/6 times 1/6, five times, so it's 1/6 to the 5th power. So you just multiply out the probabilities of each individual occurrence. Likewise, here you just multiply the likelihood of each observed data point. So you multiply this value here times this value times this value times this value and so on until you get all of your data points. So let me write that out in equation form, and I will keep our notation here and use f for our likelihood function. So our total likelihood here is just the product of each individual likelihood here. So, point 1, point 2, all the way out to point n. Or in fancier notation here, this symbol here means the product. So the product of point I equals 1 to I equals n of f of x sub I. Okay, so we need to find the derivative of this expression here with respect to mu and sigma. I think I'm going to actually work this out just for mu. Sigma is more of a pain, so I'm just going to do mu, which is a bit easier. But even mu, as written here, can be really difficult because you have n product rules. If you know calculus, you're going to have to do product rules for all of this. And embedded in that is a chain rule, so this becomes kind of nasty pretty quickly. But we're going to take advantage of a fact that if you take the log of this, the log of a product becomes the sum of the logs. So that'll be nice since we get rid of the product rule. And we don't change the position of a maximum. So if I come down here just for the time being and go plt.plot x comma y, we'll get back our, this was the graph we had up above. If I take the log of this, so I go, so notice here that the center is at x equals 2. If I take np.log, you notice that the maximum is still at 2. So we don't really shift that if we take the log. There's another advantage in that if you're doing numerical things, if we come back up here to this plot, if we go out to a high values of x, either plus or minus x, this function goes to 0. So if we have points out there, you're essentially going to be multiplying terms by 0, which forces that down to essentially 0. So that causes a problem with the computer. So you notice this, you're always, you have the absolute value of these y values are still pretty decently sized, so you won't get multiply or divide by 0. So we're going to take the log of that, of this here, and we're going to take advantage of the fact that the log, let's do this, log of a times b is equal to log a plus log b. So let me write that out explicitly here. I'm just going to copy this formula again and then show how this is going to work out. Okay, so this is the expression we want, the log of our likelihood function, and that's equal to this monstrosity here. But we could use this, where is it? This kind of algebraic identity here to write it like this. So the product becomes the sum, and the log is now inside of this summation. Now it doesn't look like it, but we've actually simplified this problem a lot. And I'm going to work out what the answer is with respect to mu here, and you'll see why in a moment. So we want to calculate the derivative of this with respect to mu, set it equal to 0, and then solve for mu. So explicitly down here, this is what we want to calculate here, the derivative with respect to mu, set it equal to 0, and then solve for mu. Now, and I am going to, when I upload this, I'm going to clean up the text here, so it's kind of more of a written description as well as this video. So again, we're going to take advantage of this relationship here, log of AB is equal to log of A plus log of B, to get this kind of isolated. So let me do that. So we have this, and then notice here, log of e to the log of e to the x is just equal to x. So we can get rid of this e and bring this down as not as an exponent, just as a term. So let me write that out. Okay, so this is what we're left with. Now let's calculate the actual derivative. That's pretty easy because this term contains no mu's, so this term is 0 when you take the derivative, and we're just left with this. Oops, there's a typo here. I gotta get rid of this log here. Where is it? Where is it? Where is it? Log. Here it is. There we go. So this is what you get after taking log of e to this expression here. You get rid of the log and the e. You get this. As I just said, this is 0 when you take the derivative. So we're just left of taking the derivative of this term. So let me just write that out. So we have this now. Again, this is 0. And now this is just a simple, what's the term? Chain rule. So this is going to become minus 2 times a half, so just minus 1 times this expression here, x sub I minus mu over sigma to the 1 power, because we're taking the derivative, and then we need to take the derivative of the inside with respect to mu. So I'm going to write out what the result is. So this is what we get for the derivative. Again, this comes from taking the derivative of the inside of this term here. The minus signs cancel out, and the sigma becomes a sigma squared. Since there's a, this is the expression now, and since there's a sigma squared in each term, we can just multiply it through. So this goes away here, and sigma squared times 0 is 0. So again, sigma goes away, and down here I just kind of broke this into 2 terms. So it's the sum of all of our x sub i's plus the sum of mu, but there are no indices here. So this term here is just mu plus itself n times. In other words, it's n times mu. So we have this, and you can see this is basically going to give us mu is equal to the mean of our samples. So this is the answer. This is the mu that maximizes the log likelihood or the likelihood, and that's how you calculate these values of mu. And you do the same thing for sigma. Again, the math is a little uglier just because more product rules, but it turns out, as we talked about before, that the mu is not the mu, the sigma is just the standard deviation. So if we come back to our original notebook, where is here? So we're doing the same thing for this monstrosity here. Now there are 3 variables. You have theta, you have mu, and you have sigma. So the math is just a lot uglier, but that's basically what the authors were doing with the same process, and you get these equations which we listed here. And obviously the results here are a lot uglier than for the normal distribution, but again, the original expression for the distribution function, oh, where was it? Up here somewhere. You know, was a lot uglier. So that's not surprising in and of itself. So I'm not going to bother with an outro for this video. Individually, I think the pieces that kind of go into this are pretty simple. It's just, again, as I said in the introduction, chaining them one after another. If there's a missing gap somewhere, it can kind of throw a wrench into the works. So I'm going to clean up this notebook that we just did because it's just kind of, just a string of equations. I'll put it on GitHub even though there's no real coding there, just so that there's kind of a written description of what we did here. Again, if there are any questions, please feel free to leave them in the comments, and I will see you later.